So last time we were midway through this proof that the equations of motion, i.e. field redefinitions, can be used to simplify the theory. And I stated last time that really all we have to worry about is the change to the Lagrangian. But when we looked at the path integral to do things properly and make a change variable in the path integral, it wasn't just the Lagrangian that changed. The Lagrangian changed, and we could set up our field redefinition to do what we want. But there was also changes to the Jacobian in the source, and that's what we had started to talk about last time. So when I look at the change to the Jacobian, which is this thing, we could write that as a ghost Lagrangian. And the argument for why we don't need to worry about this is as follows. So the effective field theory is going to be valid for small momentum. There's an expansion, and there's some scale introduced by the higher dimension operators, lambda nu, and we're looking at low momentum relative to that. In the particular case that we're dealing with, this parameter eta had dimensions, and so lambda nu was 1 over root eta. And we'd put factors of eta in front of our higher dimension operators, so that's like putting 1 over lambda nu's in front of those operators. And the reason that we don't have to worry so much about this ghost Lagrangian is that these ghosts are going to get mass that's of the size lambda nu. So what that means is that the ghosts, along with perhaps other particles that are up at the scale lambda nu, are things that we don't have to worry about. And we can effectively integrate out the ghosts from the theory in the same way that we would think about removing some particles that had masses of order lambda nu. So I'll show you why they get masses of order lambda nu in a second. So let's do that by way of picking a particular example. So far, we've kept things fairly general without specifying what this set of fields that's in this thing that we called T was. We just left it as an arbitrary thing. Let's pick a particular T. The argument here is actually fairly general, but I think it's easier to see it for a particular example. So if we pick this to be T, we have this term, which has no relation to T. That term is important. And then we have the terms from this. And so we'd have a ghost Lagrangian that would look like that. So this here is going to be the mass term. And so far, it doesn't look like it has the right dimensions. And that's because we've got our kinetic term, if you like, with the wrong dimensions. So if we want ghost fields of standard dimensions, or canonically normalized kinetic term in this case, we would take C and rescale it to C over root eta. And if we do that, then this does become a lambda nu. So that removes the eta in the interaction term here. It removes it from this kinetic term that happened to be there. And then the only place that the eta is showing up now in this case is in this mass term. But now you see explicitly in terms of these ghost fields that they have mass lambda nu. Okay? And that's just what I was claiming. So the important point here was that you did need this 1. This 1 was playing a very important role in this argument. If the 1 wasn't there, this wouldn't work. And that 1 was related to something that was part of one of our starting assumptions, that when we made the field redefinition, that the 1 particle states would stay the same. So if you look back at what our field redefinition was, and you trace back where that 1 came from, we had a field redefinition that was of this form, and this guy was a function of other fields. But we always had this term. And that term was related to the presence of this 1, and that was important for this argument. OK? So there has to be a term that's linear in the new field. We want the same 1 particle states. So these ghosts, as you know about ghosts, always appear in loops. And so if you want to think about removing this massive particle, it's like a massive particle that occurs in some loops. It's really just like that. So it's just like a heavy particle that you would remove from the theory that would only appear in loops. And we're going to discuss exactly how that works and how to remove heavy particles that appear in loops in detail a little bit later. So for now, that's enough detail for number 2. So is there any questions about that? OK, so the change to the Jacobian is effectively a massive ghost that we could integrate out of the theory. When we integrate it out of the theory, it would shift the values of the couplings in the Lagrangian, but it doesn't have any impact that can't be absorbed in other operators in the effective theory. So then the final thing we have to worry about is the source. So there was this term with J phi dagger, and what about taking, when we take, there was an extra term with J phi dagger that we had last time. I'll remind you what it looked like. So in our path integral, we had an exponential of a bunch of stuff, but then there was one final term that was induced that involved J phi dagger from the field redefinition. So when you take derivatives with respect to J phi dagger, there's sort of the usual term that we want a source, and then there's this new term. So what about that new term? That's the final thing we have to worry about. And this is where it's important that we're actually considering observables. So we need to consider observables. So let's start by considering some Green's functions, or time order products. So I'm just taking a string of fields. I could have some other fields here as well. I'm going to make my life a little easier by taking the phi to be real. And that's just for notational simplicity. I could write phi daggers and phis, but so when we make the field redefinition, what happens to that time order product? So this is one way of thinking about these extra terms from the source. So So if you take functional derivatives with respect to the other piece that involves j phi, you get phi's. If you take them with respect to that piece, you get extra eta t's. Or you can just think about making the field redefinition directly in this matrix element. And you'd have a matrix element that looks like that. So it's not at all obvious that these extra pieces that involve fields can't change the value of this Green's function. And in fact, they will change the value of that Green's function. But the important thing is that we have to consider observables and not just Green's functions. So when we're going to think about observables, we should think about the LSZ formula, which connects Green's functions to S matrix elements. So let me remind you about that. And I'll remind you what it looks like for some fixed set of fields, which are scalar fields, but we could put fermions in it as well. So what this says is if I look at this, so it's an integral over the space-time. I'm sticking in particular momentum for the particular fields. And if I look at it, if I look at the leading term, the leading pole term, as the particles are taken on shell, then that's an observable, known as the S matrix. So some number of these particles are incoming, some number of them are outgoing. That affects the sign that I put in this plus minus. I'm not trying to be too detailed about for which ones are outgoing, which ones are incoming, but some of them are incoming, some of them are outgoing. And for each one, I want to strip off the leading pole. I want to look at the coefficient, and it has to have a pole. So this is a product over all particles. We really need to pole in all the different cases, for all the external particles. Okay. So there's other. If I wanted to make this an equality, I'd say plus dot dot dot. There's other terms, and the thing that's observable is the coefficient of these poles, not the z, but this thing. So if I make changes to my theory and they affect this thing, but get canceled by this thing, as long as they don't affect this thing, we're OK. And the claim is that we make this change to the source, and it won't affect the matrix element of S, the S matrix. So again, we can do some examples, and I think the examples fairly quickly are convincing that this is the case. So we'll do 3 different examples. First, a rather trivial one. What if t was just phi itself? So t is just phi. So this is just 1 plus eta phi. So if you think back when we have t, this was the form of the term in the Lagrangian. So this is just eta phi del squared phi. So it's just changing the kinetic term for phi. If we look at our matrix element, we're just getting a factor of 1 plus eta for each of the fields. So let's say we had 4 of them, so I don't have to. So say I had 4 of them. If I had n of them, it would just be to the nth power. But if I have 4 of them, then there'd be to to the fourth power, and I just get this extra prefactor. And it looks like it's changed g. And indeed, it has changed the left-hand side of this equation. But when we calculate the z factor and we canonically normalize, if you want to think about it that way, then we would exactly cancel off these 1 plus etas. So the root z here is going to be 1 plus eta as well. So when we look at this is just the residue of the free propagator, and if the residue gets changed when you change the kinetic term. So that doesn't do anything to the S matrix. So that's one way we can be protected. We change the left-hand side, it's compensated by a change to the z and leaves S invariant. Let's do another example, a little more non-trivial. So let's just take some cubic term in our field redefinition. So this is like having a phi cubed del squared phi term. So this extra term will give rise to extra terms in the time order product, and let me just write one of them. Again, thinking of it as a 4-point function. So let's just imagine I look at the change that comes from changing the fourth guy. So there's other terms from changing phi of x1, phi of x2, and phi of x3, but if I work to order eta, then I change one of them at a time. And we're only working to order eta here. So the claim is that actually that this matrix element has no effect on this structure. It can affect the dots, but it's not going to affect the leading term, and that's because having a phi cubed means that you're not having a one-particle state. So if you tried to draw it as a Feynman diagram, in position space, you'd label these external points, and you inject momenta there. And then we label point 4, but there's 3 fields there, so maybe we have to tie it up like this or something. And when you look at asymptotically what's going to happen from having a phi cubed, you do not get a single particle pull from a phi cubed. So this guy's less singular. Has no single particle pull, and hence gives no contribution to scattering. Yeah.
As far as the theorem goes, this last step that you're showing is pretty much by hypothesis, right?
In what sense?
Like the hypothesis of the theorem is that field redefinition does not change your one-particle states.
That's right. That was an assumption.
I mean, that's exactly just what you're. Is that the same as what you're?
It's the same, yeah. It's effectively the same, although it's being more careful about what the statement of that means, right? Because it's, I mean, you're changing the residue, but you're not changing the S matrix.
Right.
Yeah.
Okay, this is what I was thinking when you said that.
Yeah. Right. Yeah. So really, the statement of, so instead of saying, I could have been a little more careful. So instead of saying that the hypothesis of the theorem is that it wouldn't change one-particle states, what I should have really said is that there's a linear term in the field redefinition. Yeah. Which now I'm showing you is equivalent to not changing the one-particle states. And let's do one final example, just to sort of rule out all possible things we could think of that are different. So what if we had a derivative, a del squared phi prime? So then we would do the following. could add and subtract a mass term. The reason we would want to do that is if we looked at a term like this, it's again less singular than this term. If this term is giving the one particle states, this term has got a factor of the propagator upstairs. So if you look for a pole that would come from that term, it's canceling out. You get p squared minus m squared over p squared minus m squared. So there's no pole from this term. And this term is, again, just of the type that we, from our first example. It's just like shifting phi by some constant. So probably to get dimensions right, I should put some factors of eta in here. So again, something like that doesn't change anything because it can be decomposed into something that has no pole and then something that's just a shift. OK? So as long as you have this linear term in your field redefinition, and it doesn't have to be even have a trivial, it doesn't have to even have a trivial prefactor. You could have 2 times phi or whatever you like, because that'll cancel out when you normalize things correctly. As long as you have that linear term, you're fine. And you don't have to worry about changes to the Jacobian or changes to from the source term. So you just have the changes to the Lagrangian to worry about. Don't have to think about the path integral. Just make field redefinitions on the Lagrangian. And that's what you'll get some practice with on the problem set.